Okay, so let me first thank both organizers for their very kind invitation to this meeting, and as well this was my first opportunity to visit South Korea. So I will speak about a topic which is not much related to math biology, but rather to cross-diffusion. And basically my talk will be in two parts. So I will first, besides recording what is this thin film Muskat problem, recording some basic things about the existence of solutions, and then I will move to large time behavior and self-similar solution. So all what I will be talking about today are joint works with Bogdan Vasile-Matyok from the University of Hanover. So what is basically this Muskat problem? So it describes a motion of two immiscible fluids with different densities, rho plus minus for the two fluids, and different viscosities, and in a porous medium. So I guess at the very beginning it was a model for describing the intrusion of water into oil. And these two fluids are subject to gravity and capillary forces. And just drawing a simple drawing of the situation. So the porous medium is something like this, with the horizontal direction x and the vertical direction y. So the bottom of the porous medium is at y equals 0. So above this medium you have a fluid which is assumed to be at the 8th y, which is f of tx, and it is assumed here that this fluid, that the boundary of this fluid is a graph, so that indeed it can be written written y equals f of tx. And so here you have the lower fluid, and then above that fluid you have another one, and the total age of this is h of tx. And again the upper boundary, and above you have air, for instance, or whatever, and again the upper boundary here is assumed to be a graph. So once you, so this is exactly the picture written. So what is the original Muskat problem? It is actually a system which is coupling two evolution equations for these two quantities, these two eights, f and h. But in addition you have two equations which describe a quantity which is inside, which is defined inside the fluid, and which is related to the pressure of the fluid. So this is this U plus minus, which is the pressure plus gravity terms, and the velocity of the fluid is related to this quantity by Darcy's law in this way. And these U plus and U minus, they actually solve elliptic equation in these, in these moving domains. So, and in addition you have some continuity properties at the boundary. So I will not write the full system, but it is actually a rather highly nonlinear initial boundary value problem, and with moving boundaries, so it is something which is quite complex. So in an attempt to simplify this model, one possibility is to assume that actually the eighths of these two fluids are very small, and to use what is called a kind of lubrication approximation, and to find an approximation which is in some sense simpler. So this is done by assuming that you have a small scale, so epsilon, which is, let's say, the ratio between the typical horizontal side and the typical vertical side. And then so you rescale all 8 by the same quantity. You rescale time as well, so that somehow it is large time behavior. and a formal expansion, asymptotic expansion in powers of epsilon, which was performed by Escher, Mathieu, and Mathieu, gives you, to first order, two equations which only involve F and H, the eighth of the two, so F being the eighth of the first fluid, H being the total eighth of the fluid. This expansion with epsilon allows you to determine actually U plus and U minus directly in terms on F and H, and then to replace in the equation. And so what you end up with are these two system of two equations. Actually here the red terms with G being the gravity constant comes from the gravitational forces, while the blue terms come from the capillary forces. So I will neglect throughout this talk all these capillary forces, so I remove the blue terms and end up with something which is a little bit more tractable, which is system of two parabolic equations for F and H. And already on this system you remark that first this is a degenerate parabolic system, because when F vanishes there is no diffusion here. Sorry. And when H vanishes, F has to vanish also, because F is below H, and so the second equation is also degenerate. And if you look here at the diffusion matrix, then you have a full diffusion matrix here. So this is a degenerate parabolic system with full diffusion matrix, and you have in particular cross diffusion here, this F dxH and this F dxF here. Well, anyway, this system has some rather interesting properties. So first of all, it's quite easy to see by applying at least formally the comparison principle that F has to stay below H. If you have the right boundary conditions, then owing to the positivity, you have conservation of matter, so conservation of both F and the total eight of fluid. And as noticed by Escher, Mathieu, and Mathieu, you have also an energy which decreases along solution to this system, which is simply the L2 norm of F plus the L2 norm of H multiplied by the right coefficient. And a final remark about the system is that if, for instance, F is equal to 0, so if you assume that in fact you have only one fluid, there is so this term cancel, there's no F here, and the equation, the above system reduces to a well-known parabolic equation, which is the porous medium equation with power 2 here. So that in some sense, beside this, the physical derivation of this model, which comes from this thin approximation of a Muskat problem, it can be seen as a natural extension to two fluids of a porous medium equation. So this is one thing. It turns out that this way of writing the system in terms of F and H is not the most convenient, and it's better to introduce in fact the eighth of the second fluid, so meaning to introduce this quantity G, which is simply H minus F. And then if you do a little rescaling, the system now reads as follows. So it's dTF is dx of F dx of 1 plus R eta square F plus G, Rg. So what's one thing, and dTg equal to R mu dx G dx of eta to F plus G. And here for simplicity, I assume that X is in R and T is positive. So there is no boundary condition. And I take initial conditions which are non-negative. And thanks to this rescaling, in fact, I can assume that both have integral equal to 1, which will play some role later on. And the parameters are positive, eta is positive, and r mu is positive. So, of course, even doing this, this change, so replacing H by G, well, you still obtain a degenerate parabolic system with a full diffusion matrix. And from this point of view, this is not really better than the first one. What is somehow a little bit nicer is that the system is a bit more symmetric with respect to F and G than the previous one, which was clearly not very symmetric between with respect to F and H. But and it turns out that so we keep some of the properties which were already on the original on the previous version, meaning that if F0 and G0 are positive, then the two H stays positive. Since we are in R and we assume that in principle F and G decay at infinity, then we got conservation of mass, which is obtained simply by integrating the equation, so that F of t and G of t are probability measures. The energy functional is still the same. Of course, now there's this parameter eta, which come into play, which mainly comes from the fact that from the rescaling to have unit-valued integrals here. But this is somehow the same. This is still f time coefficient, and this is more or less a weighted sum of the two eights. And this is the exact dissipation here. But it turns out that the nice thing of writing the system in this alternative form is that in fact there is another decaying functional, which I call an entropy functional because it involves f log f, as in Boltzmann equation, but which is in fact a Lyapunov functional, and it turns out that this function is also decaying, is also a Lyapunov functional for the system. So there is a second, with this formula for the system, you find some additional information. Information which is not so bad because it gives you some H1 information of both F and F plus G. It turns out that this writing of the system has another advantage in the sense that it reveals a variational structure of this model. In fact, if you look at the energy, which I recalled here, which is the sum of the L2 norm of F and an L2 norm of F plus G with some suitable weights, then you can write the system as dTF equal dx of F times dx of the derivative of the energy with respect to F, and more or less the same for the G equation up to some factor which you put in front of the derivative of G. And this form here is reminiscent of the fact of being a gradient flow of this energy, not with respect to the usual L2 norm, but with respect to some fashionable distance, which is the two Wasserstein distance metric on the set of probability measures with finite second moment. So simply, at least formally, this is this expression gives you this intuition here. So I just recall what is this Wasserstein distance. I mean, if you take two probability measure with finite second moment, you take any probability in R2 which has first marginals mu and nu, and then you compute the integral over R square of x minus y square with respect to this probability measure. You take the infimum, and then this gives you the square of this distance. Okay, but this is not somehow, I will not enter into details into this. The important thing is that this gives a rather nice way of constructing solution by a variational approach, in the sense that I introduce this energy here. So I have the usual energy, and here I have a distance between U and Fn and V and Gn. Assuming that I've already computed, so okay, let me start again. So I take a time step tau, and I assume that I have computed Fn and Gn, which correspond, let's say, to F and G at time n tau, and I want to compute the next step, and I compute the next step by by minimizing this functional on this convex set, which is simply the set of probability measure with finite second moment and which belong to L2. And solving this minimization problem will give me another point, which I call Fn plus 1 and Gn plus 1. And in fact, if I start from F0, G0, which are the initial data, then with this I construct a sequence of minimizers. And after this, when I define function f tau of t, g tau of t to be piecewise constant function in time starting from this sequence of minimizers, then in fact what I can prove is that there is a sequence tau k converging to 0 and a couple of functions f and j which with values in this convex set such that this sequence here converges to this couple Fg in a rather weak topology. And the nice point of this F and G is that first there are a weak solution of this system. So weak in the usual sense that you multiply by a test function and you integrate once by part. And they have the following regularity, so they are bounded with values in L2 and square integrable with respect to time with values in H1. And they have some mere continuity property in a negative space, so that they take the right initial condition. Sorry. And finally, one can show that this solution verifies energy and entropy inequalities, which are of the same kind as these ones here, which I wrote. So something of this kind and something of this kind. Just a comment about the proof. Well, first, the existence of a uniqueness of a minimizer is rather easy because, well, the energy is simply positive and convex. So, I mean, this is not very difficult. What is a bit more difficult is that we are minimizing in a set of square integrable function, and it's quite clear that in the equation you have derivatives. And so the minimizers which we obtain here, the Fn and Gn, they are only in L2 and they are not in H1. So I mean this is not possible to do this computation right after the minimization process. So one has to improve the regularity of the minimizers and to show that these minimizers, they are not only square integrable, but they are also in H1. And once you have shown this, by an argument which is borrowed from a paper by Mathès, Mancan and Savary, then you can identify the Euler-Lagrange equation satisfied by these people, and then you prove time compactness and convergence by, let's say, standard method of calculus of variation. As a side comment, so in fact, even if we include the capillary term, which I left away in this model, in fact, the full system has the same gradient flow structure. So somehow the technique can be used to show existence of solution with the capillary term included. What is lacking in this is that we only have existence by this technique, and we do not have uniqueness. And even using other technique, well, uniqueness is, as far as I know, still an open problem for this system. Two of the problems for which we have some formal arguments but not yet a full proof is that because this is a degenerate parabolic system, so we expect finite speed of propagation, and this is likely to be true. And it turns out that there is a third Lyapunov functional which involves an L3 norm, but up to now this is only a formal computation, and we have not been able to justify that the solution we construct via our approximation satisfy also this additional regularity property. And as a final comment, so one can also study this system using with tools from a parabolic system and obtain the existence of classical solutions, but of course as long as f or g does not touch 0, because then the solution ceases to be classical. So let me now go to the second part of my talk, speaking about self-similarity and large time behavior. And since you might not be fully familiar with large time behavior of a porous medium equation, let me first recall what is known for the simple porous medium equation, which I recall can be obtained, let's say, by taking here g equals 0. If you take g equals 0, you obtain dtf equals df f dxf, which up to a factor 2 is exactly this equation over there. So if you look at this equation for w, dtw equals d2xw squared with an initial data which is integrable and has an integral equal to 1 and is non-negative, then it's well known that the only integrable stationary solution to this problem is 0, which makes it, so the dynamics is expected to be trivial, and indeed you can prove that the L infinity norm of W converges to 0 at the rate t to the power minus 1/3, while its L1 norm stays constant. So what happens is that somehow you have a constant mass, but the amplitude is reducing, so you have a spreading of mass, which is a consequence of the diffusion. What is interesting with this equation here is that you have a scale invariance, in the sense that if W is a solution, then if you multiply W by A, you multiply the variable x by lambda, and if you multiply the t variable by A lambda square, then this is still a solution. So this is one scale invariance. And in fact, even if you take A to be lambda, this is still a solution again, but in addition its L1 norm is still 1. So this particular rescaling preserves also the L1 norm. And then it's rather natural to look for solution which could be invariant with respect to this scale. So these are solutions of that form, and it turns out that there is only one solution of that form which is explicit. So it is simply t to the minus 1/3 b1 x to the t to the minus 1/3, and b1 here, which I will call the profile, is simply given by an inverse parabola which is truncated on its positive value. And the real number CR1 here is just, it can be computed explicitly, and it is just made such that the L1 norm of this guy is exactly equal to 1. So what is to remember from this slide is that there is only one self-similar solution solving the equation. And then a classical tool in the large time behavior study of problems where you have a self-similar solution is in fact to change variables in order to move from let's say something which is time dependent to something which is stationary. So more precisely, if I introduce y, which is x times 1 plus t to the minus 1/3, and s, which is log to 1 plus t, and if from w I define a new function which is defined by this formula, then v solves this equation, which is nothing but the porous medium equation to which a drift term has been added here. But what is interesting in this new formulation is that now the Barnblatt profile B1 is a stationary solution here. So it was B1 was used to make a self-similar solution of the porous medium equation in the original variable, and now it is a stationary solution to this, and so it's better to study things on the V equation, because it's usually easier to show that something converges to a stationary solution than to compare two time-dependent functions. And in fact, what can be shown is that whatever value of p which you choose, then v of t minus b1 converges to 0 in any LP norm. And if you go back in the original variable, so for the function w, this means that w behaves exactly like the self-similar solution. Even depending on the initial data, you can find decay rates of the distance between v of t and b1 in some suitable LP norm. And I refer to papers by Camin, Friedman and Cabin and Cario Toscani and many others for more details about this convergence. Well, since as I have mentioned, this equation can be seen as an extension of a porous medium equation to, let's say, two fluids, well, it's rather natural to wonder whether there are self-similar solutions for this problem. And in fact, it turns out that the first thing we notice is that it has the same scaling invariance as the porous medium equation which I mentioned. So the thing is whether we can construct self-similar solution and possibly study their stability as is for the porous medium. So self-similar solutions are going to be of this form, t to the minus 1/3 time f. So self-similar are 1 over t to the 1/3, capital F, capital G, x over t to the 1/3. So we are looking for, and in very much the same way as I explained for the porous medium equation, that it was better to change variable to find something in to get some stationary solution. The first step I'm going to perform is a change of variable. So I use self-similar variables, and then I end up with this system, which is nothing but the same system as before, plus an additional drift term. And we aim at looking for a stationary solution to this equation, stationary solution, so F and G, and an important requirement is that they both have L1 norm equal to 1, because this is the this is a conserved quantity. So this is one important property. So when doing that, so I'm looking for stationary solution to this, and one obtained rather easily that F and G should satisfy these two equalities. So F times dx of this quantity is 0, and G times dx this quantity is equal to 0, still with the constraint that F of G have integral 1 and are non-negative. So it's quite clear from this equation that when F is equal to 0, this does not give anything. I mean, I just know F is equal to 0 and I lose information here. And as well, when G is equal to 0, well, this does not give, well, I cannot use any information coming out from this. Meaning that there are two sets which are going to play a very important role in the analysis. This is the positivity set of both F and both G. Because if I am in the, if X is a point in the positivity set of F, then I can use the information coming from this derivative being to 0, and similarly if X is a point in the positivity set of G. And in fact, one can prove the following. So if you take an interval where both F and G are positive. So this means that this derivative here is 0 and this derivative here is 0. So we get that eta squared of f of x is a quadratic polynomial, and the same for G here. Now, if I is an interval which is in the positivity set of F, but not in the positive set of G, so then G is going to be 0 in that interval, and I use the equation for F here, so the first equation, and I get that F is a quadratic polynomial. And the situation is reverse if I is an interval which is included in the positivity sets of G and the positivity set of but not in the positivity set of F. Sorry. So, and of course, these three situations are disjoint situation, but they can occur for the same solution. So one has then possibly these three possibilities for a single solution, but then there are going to be compatibility conditions between these three things. The parameters A and B are not necessarily the same here and here. And on top of that, so one has first to find whether all this is compatible. And on top of that, one has to check that the thing that we construct has exactly mean value, has exactly integral 1. So this can be done. This is a little bit painful. This is solving algebraic equation or system of nonlinear algebraic equation of 5 or 6 equation. But the outcome is the following. So if I fix my three parameters R, eta, and R mu, the first thing we can prove is that whatever the value of these parameters, there is a unique even solution F naught, which I call F naught G naught. So it is even, it is unique, there is only one, and it can be seen as a minimizer of the rescale energy corresponding to, so this system has a rescaled energy, and if you minimize it, you will obtain the unique even stationary solution. So it is even exactly like the B1 here for the porous medium equation. But then it's not the end of the game. It turns out that if R mu is outside a certain interval, then there is a continuum of stationary solution. So FL, which I indexed by L here, where L is in a closed interval lambda. So if L is 0, then this is the unique even solution. If L is non-zero, FL and GL are non-symmetric. Well, this is related to the uniqueness of the evenness. And in fact, either FL or GL has a disconnected support if L is not a point on the boundary of lambda. And in fact, you can find also some other values of critical values of R mu. Then the boundary points for the stationary solution corresponding to L plus or minus, they have connected support. So in general, just to include the case where there's only one solution, which is true if R mu is in this interval, then I put lambda reduced to the singleton 0 if R mu is in there. So just as an example of a symmetric self-similar profile, this is what you can have. And as you see, it has this one has disconnected support because here there's nothing. And this is an example of a non-symmetric one, and it has a connected support. So the blue one and the red one have both connected support. The black one is simply the sum of both of them. So it corresponds to the total height of the fluid. And they have compactly supported support both. And this is another non-symmetric but with a disconnected support. Okay, so then the next step, having, we have quite a number of solutions. So the first remark is that, of course, this is very different from the porous medium equation for which there was only one self-similar solution. Here, in quite a number of cases, we have not only one, but a continuum of self-similar, of stationary solution. So the question is, can we say something more about whether they attract the dynamics or whatever? So the first thing we can say is that because we have a Lyapunov functional corresponding to this, is that these stationary solutions are attractors for the dynamics in the sense that the omega limit set, that is the cluster point as time goes to infinity of any solution to that, is only made of stationary solutions. But because we have a continuum, we could have a continuum, this does not allow to conclude that there is only one possible limit. But here it turns out that we have a piece of luck in the sense that if we compute the values of the rescaled energy on the stationary solution, well, it turns out that this is a function which has a very special shape in the sense that it is first decreasing from L minus to 0 and then it decreases from 0 to L plus. Meaning that if you fix the energy, you have at most two stationary solutions with the same energy. And since due to the evolution, since the energy has a limit, then, and we know that the omega limit sets are discrete sets, since this is a discrete set which can only contain two elements, then actually we get the convergence, in fact, from this monotonicity and from the connectedness of the omega limit set. Something which, of course, we do not know, even if we are in a case where we only have one stationary solution, is whether we have some decay rate. And of course, another important point is, so thanks to this monotonicity of a rescale energy, we know that we have convergence to one steady state, but of course we do not know to which one. Of course, if you start with an even initial data, well, evenness is preserved and you will converge to an even initial data. So it's rather natural to ask whether some non-symmetric initial data, some non-symmetric stationary solution could be attractors. Because in addition, we know that the even stationary solutions are minimizers for the energy. So let me first show some evolution in the symmetric case. So where you see that well, there is a hole that creates here and is going down up to well, up to the end of up to touching 0, but it's going slowly. And here you see that you have some singularities which mean that which have developed, which means that as expected from the degeneracy, that the solution is Lipschitz continuous, but it is not smooth. Okay, so maybe I will not wait until things touches 0, unless you will maybe fall asleep before it arrives, but okay. But then this is what it does in the end. And the next thing was just to check. So the other is where we start with something which is non-symmetric. And so we observe first that the two bumps, they come close together, which anyway we can predict because all the self-similar solutions, they have a common part of a support. So anyway, you have, even if you start with two bumps of fluid which are far apart, well, they have to collapse. So you have this nice singularity here of a gradient, which is expected. And in fact, the evolution will basically will stay on this non-symmetric stationary solution, so that it seems that not the dynamics is not governed by only the even solutions, but that some of the non-symmetric ones play a role in the large time behavior, which of course makes it even more difficult to identify which one is a limit. Thank you very much for your attention.